Imagine this. You're floating in space, not the neat, postcard kind of space with polite dots of starlight, but the raw, endless dark where your breath is loud enough to feel like an intrusion. Ahead of you, the darkness isn't empty, it's solid. Not because something's blocking your way, but because the light itself has pooled here, like a glassy wall, shimmering with every color you've ever seen and some you haven't. It's not a wall you can touch if you moved toward it. It would recede, always staying just far enough away to remind you that this isn't your place to reach. Hello, and welcome to Sleep Science, where curiosity settles in silence, and science is told in the breath of dreams. Tonight, you don't need to remember anything. Just listen, let your jaw go slack, feel the weight in your limbs, and let the thoughts settle. What happens when you reach the speed of light? You've heard the number before, 299,792,458 meters per second, but numbers don't make your chest tighten the way this wall does. This is the horizon of the possible, and we've been told for over a century that nothing with mass can break it. Einstein didn't set the rule because he liked speed limits. He stumbled on it while trying to explain why the laws of physics seemed to work for everyone, everywhere, no matter how fast they were moving. Imagine being on a moving train, tossing a ball straight up, and it's still coming back to your hand even though someone outside the train swears it's arcing forward. Now swap the ball for light, and suddenly, the universe is forced to bend time and space themselves to make the math work. That's when the speed of light stopped being trivia and started being law. Here's the uncomfortable truth: you can push yourself faster and faster, adding more and more energy, but the closer you get to this limit, the harder the universe pushes back. Your ship, your atoms, even the electrons in your fingernails would start to resist in ways that aren't just stubborn, they're absolute. Mass doesn't like being hurried, and at these speeds it becomes a tyrant, demanding infinite energy for that last tiny push. You're not supposed to win this argument. And yet, here you are, staring at the horizon as if it might blink first. Odd fact, light, the thing you're chasing, doesn't experience time at all. From a photon's point of view, if it could have one, the moment it leaves a star and the moment it hits your eye are the same instant. It's an existence without before or after, which means if you somehow reached this speed, time wouldn't just slow down for you, it would dissolve. No birthdays, no waiting, no cause and effect in the way you know them. You wouldn't just be fast, you'd be timeless. Scientists still debate whether there's a loophole, something at the Planck scale, some exotic particle, or even a warped piece of space-time that could cheat this limit. But that's like wondering if you can sneak past a sleeping guard without knowing whether the guard is asleep, or a statue, or the wall itself. Maybe you could, maybe you can't. The fun is in asking. The wall in front of you doesn't pulse or glow with drama. It just sits there, indifferent. You reach out, not literally, but with the kind of reach that happens in your mind when you think of someone you haven't seen in years, and the wall doesn't care. That's the thing about the speed of light. It isn't a finish line, it's the edge of the rules. You can run right up to it, but the game stops there. You lean back in your seat, the hum of the ship blending with your breathing, and think about how strange it is that the fastest thing in the universe is also the loneliest. It never rests, never slows, never grows old, and it never lets anything catch up. The wall fades in your mind, but the feeling lingers. Somewhere, just ahead, reality itself is watching you try, and quietly shaking its head. The hum of the ship becomes a low purr now, steady enough to match your heartbeat, like the two have decided to sync up without asking you first. You're still in motion, still leaning toward that unreachable shimmer ahead, and somewhere in the dark, Einstein's name drifts into your thoughts, not as a textbook figure with wild hair and a pipe, but as the stubborn man he was before all the portraits, working in a patent office, shuffling papers that weren't even his ideas. He wasn't chasing fame, he was chasing the kind of why that keeps you awake at night. You picture him hunched over, calculating the speed of light without ever trying to catch it, realizing that the universe has a built-in limit, a hard stop that applies to everything, everywhere, always. The rule didn't arrive with trumpets. There was no cosmic referee blowing a whistle to tell us we couldn't break it. Instead, it slid out of the math quietly, but firmly, The equations told him something uncomfortable. If the laws of physics were to hold for everyone, moving at any speed, then light speed had to be the same, no matter who measured it. The problem? That meant time and space themselves would have to stretch, shrink, and twist to make it true. And if that was real, then the dream of going faster than light wasn't just improbable, it was structurally impossible. You shift in your seat, imagining what it must have been like to tell the world this news. People like rules they can break. Tell someone the world's tallest mountain is Everest, and you'll have climbers lining up. Tell them the universe has a maximum speed, and you'll have dreamers, inventors, and conspiracy theorists all trying to slip a finger past the cosmic doorjamb, but no one has succeeded. Every experiment, every particle smashed in a collider, every deep space probe, every scrap of stardust we've studied agrees. This is the law. Science fact. The famous equation EMC2E equals MC2EMC2 didn't start out as the crown jewel of physics. It was just a side note in Einstein's 1905 paper, one more implication of relativity. It's not really about energy equals mass times the speed of light squared in a practical sense. It's more about the idea that mass and energy are two sides of the same coin, and to get more speed, you need more energy. Energy that grows toward infinity, the closer you get to light speed. And infinity isn't on sale anywhere. Odd fact. The speed of light isn't actually the speed of light. It's the speed at which any massless thing travels through a perfect vacuum. Light just happens to be our most famous example. In theory, even gravity travels at that speed, which means the sun could vanish, and we wouldn't notice its light or its pull on Earth until about 8 minutes later. Scientists still debate whether light speed is truly constant everywhere. Some theories in cosmology suggest it might have been different in the early universe, perhaps allowing matter to spread faster across the newborn cosmos. But these are fringe ideas, the kind you keep on the mental shelf labeled maybe while you keep living in the almost certainly not aisle. You glance out the viewport and imagine explaining all this to someone who isn't here, someone on Earth, sipping tea and wondering how you're spending your evening. You tell them it's like chasing the horizon. No matter how fast you run, the point where Earth meets sky will always move away. You'd laugh softly and say, and the joke is the horizon isn't even real. It's just where your vision ends. And maybe that's what the speed of light is, the vision, line of the universe itself. The hum of the ship doesn't change, but your awareness does. You realize Einstein didn't set a speed limit to frustrate you. He uncovered it to explain why the universe doesn't tear itself apart in a chaos of mismatched clocks and distances. The rule is there, so time remains time and space remains space. Without it, nothing would make sense, not even you sitting here now. You breathe in slowly, exhale even slower, and the shimmer ahead stays exactly where it was, neither inviting nor warning, just waiting. Your hand rests lightly on the arm of the chair, but you can feel it, an almost imperceptible heaviness settling into your bones. Not the kind that comes from fatigue, but the kind that makes you think your atoms have decided they're not interested in going any faster. You wouldn't notice it on Earth. Even at orbital speeds, it's nothing. But here, inching closer to the ultimate limit, mass stops feeling like a passive thing you carry around and starts acting like a stubborn old landlord unwilling to budge without extracting payment you can't possibly afford. Einstein's math made it clear. The faster you move, the more your mass appears to increase. It's not that you're gaining actual matter. You're not suddenly made of extra atoms, but your resistance to acceleration grows. Push a parked car, and it eventually moves. Push the same car uphill, and it takes more effort. Now imagine the hill becoming steeper every step you take, until the slope is vertical, and every bit of energy you throw into the push just disappears into the climb. That's what your mass is doing right now. Science fact. Even the Large Hadron Collider, that vast underground ring in Switzerland designed to smash particles together at ridiculous speeds, has never made a proton reach the speed of light. It gets to 99.999999%, which is like running a marathon and stopping a single hair's breadth from the finish line, but that last fraction would require more energy than exists in the observable universe. The universe, it seems, has a very expensive toll road. Odd fact: cosmic rays, those high-energy particles from space that sometimes slam into Earth's atmosphere, can carry more energy than a fastball pitched by a professional baseball player. They get incredibly close to the speed of light, but never at it. Not even nature gets to skip the bill. Scientists still debate whether relativistic mass is even a helpful concept anymore. Many physicists prefer to talk about energy rather than saying mass changes. But the effect is the same. To you, the pilot, acceleration feels like hauling yourself through molasses that thickens the faster you go. You push forward, and the ship pushes back not because it's braking, but because the rules are holding. And here's where it gets personal. You start thinking about how this applies to everyday life. You've felt resistance before trying to change a habit, trying to have a conversation with someone who's already decided you're wrong, trying to keep your eyes open when you should be sleeping. That same pattern is here, written into physics. The closer you get to the thing you want, the harder it gets to move. And just like in life, there's a point where pushing harder stops making sense. You glance at the control panel not because you expect it to help, but because it's comforting to look at numbers, graphs, and flashing indicators that confirm you're still in motion. The readout shows speed measured against the speed of light, each decimal place a reminder that progress is shrinking. The leap from 80 to 90% was thrilling. 90 to 99 felt like an achievement. 99.9, you can barely feel the difference. 99.99, you could stare at the gauge all day and swear it hasn't moved. There's a slow irony here. The universe seems fine with you getting close, even brushing against the limit in your imagination, but it won't let you touch. You can stand in the lobby, but the door to the ballroom is locked. Still, you press your hand mentally against that locked door and think, maybe there's a crack. It's human nature. The hum of the ship deepens slightly, as if sharing the weight you feel. Your body is still the same, but your relationship to it has changed. Every muscle feels more anchored, more tied to the universe itself, as if space-time is wrapping invisible bands around you. Not threatening, not painful, just firm. It's the same kind of firmness a parent uses when guiding a child away from the edge of a cliff. No, not there. Somewhere behind you, countless stars are sliding away into the background, their light stretching and shifting, but you don't turn around. The heaviness in your bones reminds you that your place, at least for now, is still on this side of the wall. The heaviness in your bones is joined now by a different sensation. Time itself feels slippery, as though it's trying to slide out from under you. Seconds, which you're used to imagining as neat little steps in a row, start to feel like liquid. You glance at the clock on the console and watch the digits roll in a way that makes you doubt they're keeping pace with the ones in your head. It's not broken. It's you. The faster you move, the slower your time runs compared to someone far away, still lounging in their kitchen on Earth. If they could watch you right now, your movements would look like they're unfolding in syrup. To you, though, nothing feels delayed. Your heart still beats in the same rhythm. Your thoughts flow without drag. This is time dilation, the part of relativity that makes people tilt their head and mutter, "Wait, what?" It's not just perception, it's real. Your seconds are getting longer. The faster you go, the more they stretch. If you reached light speed, those seconds would stretch infinitely. You'd never make it to the next tick. From your point of view, nothing has changed. From anyone else's, you've slipped into a slow-motion recording that never ends. Science fact: astronauts on the International Space Station experience time dilation, just enough that they age a fraction of a second slower than people on Earth. It's tiny, mere milliseconds, over months, but measurable. For cosmic travelers at near light speed, the effect wouldn't just be noticeable, it would be dramatic. You could take a trip lasting a few years by your clock and come back to find that decades, even centuries, have passed on Earth. Odd fact: in 1971, scientists flew extremely accurate atomic clocks on commercial airliners around the world, then compared them to identical clocks left on the ground. The traveling clocks had lost a few billionths of a second, just as Einstein predicted. Billionths sound trivial, but the point is they changed. Scientists still debate how time dilation might be exploited, whether it could allow for one-way time travel into the future. You couldn't go back, but in theory, you could leap forward just by going fast enough and waiting. It's a peculiar form of escape. Run away from your own timeline, and you'll find yourself in someone else's future. You lean forward, watching the light ahead smear just slightly, as though it's tired of keeping up appearances. Your own thoughts start drifting to the people you've left behind, what they'd be doing right now. Then you realize right now is becoming meaningless. If you turned around this moment, you might find them hours older, days older, maybe more. The longer you stay at this speed, the wider the gap becomes. And there's a strange intimacy to it being on your own timeline, unshackled from everyone else's clock. It's isolating, yes, but it's also freeing. You start thinking about life on Earth, how everything there is so synchronized: meetings at 3 o'clock, dinner at 7:30, bed by 11 o'clock. Up here, none of that applies. The universe doesn't care when you eat, when you sleep, or whether you reply to that message in a timely manner. Your time is literally your own. Of course, there's a shadow to that thought. If you kept going long enough, you could return to find no one you knew still alive. Your home would be a museum piece, and you'd be the only exhibit that doesn't belong. The kind of loneliness that comes from time dilation isn't about distance, it's about disconnection. The ship's gentle vibration under you seems to stretch in rhythm with your elongated seconds. You breathe in, and the breath feels wider. You exhale, and it feels like the air has more time to leave. Maybe that's the point. Maybe this is the universe's way of saying, slow down, even as you rush forward faster than almost anything else in existence. You rest your head back and think about how strange it is that speed doesn't just move you through space, it changes what now even means. And for the first time tonight, you wonder if chasing the wall is worth what you'll lose on the way. The colors are the first thing to betray you. At lower speeds, stars are points of white or warm gold, maybe a pale blue if you're lucky. But now, the forward view is shifting in ways your mind isn't built to process. The stars ahead swell into icy sapphire, their light squeezed into shorter, bluer wavelengths as you rush toward them. The ones behind you are bleeding into long red sighs, their glow stretched thin like sunset, smeared across the whole rear horizon. It's not your eyes playing tricks, it's the Doppler effect, the same thing that makes a siren drop in pitch as it passes you on the street. Here, though, it's not sound but light that's changing pitch. Science fact. Astronomers use this exact effect to measure the motion of galaxies. When they see starlight stretch toward the red end of the spectrum, it means the galaxy is moving away. Blue shift means it's coming closer. The entire idea of an expanding universe comes from this observation. Edwin Hubble wasn't just looking at pretty lights. He was listening to the color of motion. Odd fact. At extreme speeds, the blue shift ahead becomes so intense that visible light can slide into the ultraviolet and even X-ray range. To your naked eye, that would mean blackness ahead, not because there's no light, but because the light has left the range you can see. You could stare straight into a roaring blaze of radiation and see nothing at all, which is its own kind of unsettling. Scientists still debate how much this effect could be exploited for real travel. In theory, a ship could use a massive light sail and ride photons like a wind, but the blue shift at high speed could turn your ship's forward-facing surfaces into a frying pan. It's one of those great in theory, deadly in practice ideas that litter the history of space concepts. You keep watching as the view grows stranger. The constellations you once recognized, Orion, Cassiopeia, are smearing forward into bright spears of light, while the space behind you melts into a warm, dying ember glow. It's not just beautiful, it's unnerving. These are the same stars, the same points of light you've always known, but speed has rewritten their language. It's like returning to your hometown and finding all the street signs in a foreign script. You start thinking about how this mirrors human memory. The things you rush toward the plans, the ambitions they feel sharp, intense, impossible to ignore. The things you've left behind soften, fade, and eventually dissolve into something you remember only by feel, not by detail. The blue shift and red shift of life, you suppose. The control panel pings softly, a reminder from the ship's computer about radiation levels. Nothing dangerous yet, but the numbers climb steadily as the blue shifted light ahead thickens into wavelengths you can't see but your instruments can. It's a reminder that physics isn't sentimental. The view might be poetic, but the consequences are practical. Shields, sensors, and protocols. The hum of the ship seems to carry new colors too, if such a thing is possible. There's a brightness in it now, a higher note that wasn't there before, as though even sound is being tugged forward by your speed. You imagine what it would be like to look at Earth from here, not just physically far away, but spectrally altered, shifted into a version of itself your eyes wouldn't even recognize. The wall of light ahead is no closer. That's the strange part. You've changed. The stars have changed. Even the song of the ship has changed, but the horizon remains indifferent. And maybe that's the message. No matter how much your perception shifts, reality doesn't flinch. It stays what it is, waiting for you to catch up or give in. You lean back, close your eyes for a moment, and the afterimage of those distorted colors lingers, half sapphire blaze, half ember fade, like the memory of something both lost and still rushing toward you. The colors still cling to your vision when you open your eyes again, but now it's the ship you're noticing. At these speeds, it isn't breaking apart, not yet, but the air inside feels heavier, as though the molecules themselves are being squeezed by an invisible grip. The panel edges seem to blur in your peripheral vision, not because they're moving, but because your brain is struggling to reconcile what your senses are reporting. Motion and stillness are no longer separate categories. They're layered on top of each other like poorly aligned film frames. Your body feels fine, mostly. Breathing is still easy, your heartbeat steady, but there's a subtle wrongness, a faint, almost tactile awareness of strain. The ship's frame, the glass of the viewport, even the walls you could lean against all have a kind of elastic resistance, as if they're made from a material that's only pretending to be solid. You run your fingertips along the armrest, and though it's as rigid as ever, you can't shake the impression that its atoms are tired. Science fact. At speeds approaching light, kinetic energy doesn't just make you go faster, it adds to your total energy in ways that stress every particle in your body. The bonds between particles don't snap, but the energy passing through them changes how they behave. If you could somehow keep accelerating, your own structure would resist in a way that feels like the universe is pushing you back. Odd fact, the fastest human-made object so far, the Parker Solar Probe, is still moving at less than 0.064% of light speed. And yet, at that modest fraction, its heat shield faces temperatures over 1,300 degrees Celsius. Imagine what would happen if you multiplied that speed thousands of times over. Even with no air in space to create friction, radiation and particle impacts would turn the front of your ship into a storm-battered cliff face. Scientists still debate how a craft could survive the forward barrage at such speeds. Some propose electromagnetic fields to deflect incoming particles. Others talk about a sacrificial shield layers of material designed to erode away slowly, like a cosmic bar of soap. But here, in the hum and slight vibration of your cabin, these solutions feel theoretical at best. The viewport begins to ripple, not physically, but in your perception. Light is bending differently now, as if space itself is beginning to behave like a viscous fluid around you. You're not melting, not in the sci-fi, dripping wax sense, but there's a psychological equivalent. The mental outline you have for what things look like is starting to dissolve. It's the same feeling you get when you wake up from a vivid dream and can't quite remember which details belong to reality. The ship hums in a perfectly familiar tone, but the rhythm feels slightly off. The lights in the cabin haven't dimmed, but they seem farther away. You tap the panel not because you think it will help, but to reassure yourself that the tactile world still exists. And then it hits you, you're not imagining all of it. As you approach light speed, space and time distort so thoroughly that your intuitive sense of physical boundaries falters. What's a meter? What's a second? Out here, both are in flux, bending to accommodate your motion. Your ship's shape, your own body, even your thoughts, they're not breaking, but they are participating in the warp. You take a long, slow breath. The air smells the same, slightly metallic, a trace of ozone from the electronics, but it feels denser, like it's reluctant to enter your lungs. Your hands are steady on the armrests, though your mind keeps circling back to the question, if the very structure of matter strains under this speed, how long could you stay here before solid stops meaning anything at all? The wall ahead glimmers faintly, the same steady shimmer as before, unchanged by your perception. You know better now, it's not the wall that's softening, it's you. You've grown used to the shimmer ahead, but now the space between you and it begins to change. It's subtle at first, a sense that the stars ahead are closer together, as though some unseen hand is pressing the universe inward. The effect grows until you can no longer pretend it's a trick of perspective. Space itself is collapsing along your path, every stretch of distance folding into the next like pages in a book being squeezed shut. This is length contraction, another of relativity's strange but inescapable consequences. From your point of view inside the ship, nothing feels compressed. The corridor you walk to reach the control panel is still the same number of steps. But to an observer watching you from a slower frame of reference, your ship is shorter in the direction of travel. The faster you go, the more dramatic the contraction, until at light speed space in front of you would shrink to zero, not because you've destroyed it, but because the geometry of space-time won't allow it to stay the same. Science fact. If a spacecraft could somehow approach 99.999% of light speed, the distances between stars could shrink drastically from the traveler's perspective. A voyage to Proxima Centauri, which would normally take over 4 years at light speed, might seem to take mere days. To everyone else, though, you'd still be gone for years. Odd fact. In particle accelerators, particles like muons live longer than they should because of time dilation, but they also travel farther than they otherwise could because of length contraction. In their own frame, the distance they have to cover has been physically shortened by their speed. Scientists still debate how this effect could be used for practical exploration. On paper, it sounds like a shortcut: crush the distance ahead, and you can reach anywhere faster. In practice, the energy cost and the distortions to everything around you make it more like sprinting toward a painting of a landscape, where the view gets closer, but the reality of reaching it remains locked behind the canvas. You imagine walking down the ship's narrow main corridor now, knowing that to an outsider, it might look half its real length, your own body shortened along with it. The thought is unnerving, not because you'd feel different, but because you'd be living in a reality that someone else would see as physically altered. And the oddest part is, both perspectives would be correct. Physics doesn't choose favorites here. It makes you think about the way people back home compress their own lives when they're in a rush, weeks of preparation crammed into a single day, whole relationships condensed into quick exchanges of words and glances. The universe does the same thing at high speed. It takes the long road and folds it in on itself, without asking if you're ready for the shortcut. The shimmer ahead doesn't feel quite so far now. Whether that's an illusion or an actual effect is almost beside the point. What matters is that your perception of the journey is warping. The space outside feels like a tunnel whose walls are bending inward, the entrance far ahead narrowing into a sharp, bright keyhole. You glance at the ship's readouts, distances to distant pulsars, star fields mapped by navigation software, and watch the numbers change faster than you'd expect. Your instruments insist you're crossing light years worth of terrain at an alarming rate, and yet you can't shake the truth. The wall hasn't moved. It doesn't matter how space folds or shrinks, the horizon itself stays just beyond reach. You breathe, slow and deliberate, letting the sensation settle. Space is narrowing, but you are still here, suspended inside the compression, untouched in your little bubble of time and length. The universe can bend all it wants, you'll just keep moving, feeling the tunnel close around you, one silent fraction at a time. The narrowing tunnel of space is quiet, too quiet. At first you think it's just the hum of the ship receding into the background, but then you notice another sound pressing in. It's faint, a static-like hiss that wasn't there before, curling at the edge of your hearing. You lean forward, straining to separate it from the usual cabin noise, and realize it's not coming from the ship at all. It's coming from everywhere. This is the cosmic microwave background, the afterglow of the Big Bang, usually so faint and cold it's just a whisper in the universe's static. But at these speeds, that background light is shifting up the spectrum, becoming louder, more energetic, and impossible to ignore. It's as if you're driving through the fog of the universe's birth, and the droplets are striking harder, faster, hotter. Science fact: the cosmic microwave background, CMB, bathes the universe at a temperature of about 2.7 Kelvin, just above absolute zero. But in your frame of motion, its frequency is blue shifted, making it seem warmer and more energetic. Push closer to light speed, and the CMB can rise to dangerous levels of radiation. Odd fact: the hiss you hear when tuning an old analog television to an empty channel contains a small percentage of this ancient signal. Part of that snowy static is literally the leftover heat from the creation of everything. Scientists still debate whether any material could withstand the CMB's intensified bombardment at near light speeds. Theoretical shields could block it, but every added layer increases mass, making acceleration even harder, a frustrating feedback loop. You check the ship's sensors, and the readings confirm it. The background radiation is climbing. It's still harmless here, but the slope of the numbers is steep enough to make you think about limits you can't see. Outside, the empty black between stars isn't really empty. It's full of relic photons, ghostly and ancient, and you're plowing into them like a swimmer pushing through a swarm of invisible insects. It makes you think of how the past always lingers, even when you're hurtling toward the future. Every action, every event leaves traces that may seem faint at a distance, but speed can bring them rushing back in your face, too bright to ignore. You might leave a place, or a person, or an era behind, but the universe has a way of making sure the remnants find you again. The hiss grows louder, not in volume exactly, but in presence. It's like a pressure at the edges of your skull, a reminder that you're moving through a history that predates you by 13.8 billion years. You wonder what it would feel like to stop suddenly, to let the radiation drop back to its natural whisper. Would it be relief, or would the silence feel wrong after hearing the universe's first heartbeat up close? The shimmer ahead doesn't change, but you do. You're aware now that even nothingness has texture, that even the calmest seeming vacuum carries the memory of a violent birth. And as you push forward, the fabric of space doesn't just bend and narrow, it speaks. You sit back, letting the hiss wash over you, eyes on the narrowing tunnel ahead, the thoughts settling in quietly. The past is never behind you when the universe itself carries it forward. The hiss fades into the background of your mind, not because it's gone, but because your attention shifts to something stranger, an odd, almost eerie calm in the numbers on the console. For all the shifting colors, bending space, and relentless radiation, the equations running in your ship's computer tell a story that feels still. It's as if, in the language of mathematics, you've entered a region where certain variables have stopped caring about your acceleration. Relativity predicted this quiet. As you push toward light speed, your velocity relative to the limit barely changes anymore. Each increment of energy you pour into the engines translates into less and less actual speed gain. The curves in the graphs flatten, the slopes smoothing out into near horizontal lines. You could feed the engines for an eternity and the readout would approach, but never hit the speed of light, a cosmic asymptote that forever refuses to close. Science fact: in Einstein's equations, velocity is never an independent player here. The real currency is energy, and as speed increases, the kinetic energy required rises without bound. That infinite wall of energy need is why no mass-bearing object can ever reach the limit. You're not slowing down because of friction or drag. Space itself is telling you, that's far enough. Odd fact: if you could somehow remove your mass entirely, you wouldn't accelerate to light speed. You'd instantly be at light speed. That's what photons do. But they pay for that privilege by having no experience of time, no rest frame, and no way to ever stop. You might call it freedom, but it's also a kind of prison. Scientists still debate whether the universe has other speed limits hidden in its deeper physics. Some theories suggest that the Planck scale, where quantum gravity dominates, might impose even stranger constraints. But until we can probe that regime directly, light speed remains the undisputed edge of our map. You watch the monitor and think about how human ambition works the same way. The closer we get to a goal, the harder it is to make progress, until the effort outweighs the gain. Marathon runners know this feeling. The last kilometer feels longer than the first 10. So do people chasing perfection in their craft. The first improvements are easy. The last fractions are nearly impossible. The stillness in the data feels almost meditative. It's not the stillness of nothing happening, but the stillness of everything balancing itself. You're moving faster than you've ever moved before, yet the numbers say there's almost nowhere left to go. It's like cresting a hill and finding a long, flat plateau stretching to the horizon. The shimmer ahead doesn't taunt you, it simply waits. Your engines hum at their limit, systems stable, all variables in check. In the silence between your breaths, you realize that the limit isn't a failure. It's a boundary where motion and stillness meet, where effort meets inevitability. You rest your hands on your knees, close your eyes for a moment, and let the calm in the equations seep into you. Out here, chasing the speed of light isn't about getting somewhere. It's about learning what it means to move as far as you can without crossing into the impossible. The quiet in the numbers doesn't last. It's broken by a reminder from the ship's core systems, an energy audit flashing across the main display. You glance at it and feel the weight of what it means. Every fraction of speed you've gained has been purchased with staggering amounts of energy, and the closer you push toward light speed, the more ridiculous the bill becomes. It's not just expensive, it's the kind of cost that tips into the absurd, like trying to fill a swimming pool with drops from an eyedropper while the pool grows bigger every second. Relativity makes the problem brutally clear. Your kinetic energy is proportional to a factor that approaches infinity as you approach the speed of light. Infinity is not a friendly number. If you wanted to accelerate a grain of sand to light speed, you'd need more energy than all the electricity humanity has ever generated. For something the size of your ship, it's not just impractical, it's physically impossible. Science fact. The Large Hadron Collider, one of the most powerful machines humans have ever built, accelerates protons to within a whisker of light speed. Yet pushing them that last minuscule fraction would require more energy than exists in all visible stars combined. This is why physicists speak of approaching light speed, but never reaching it. Odd fact. In the 1962nd, scientists calculated that even if we could somehow capture all the sunlight hitting Earth for an entire year and focus it on a single spacecraft, it still wouldn't be enough to accelerate a crewed vessel to light speed, not even close. Scientists still debate whether there could be exotic energy sources like harnessing the rotation of black holes or tapping into zero-point energy that could make the impossible less impossible. But so far, these ideas belong to the realm of maybe someday, rather than launch next week. You lean back in your chair, letting the energy readout scroll past like an accountant's nightmare. The ship's AI helpfully recalculates your fuel-to-speed ratio, displaying a graph so steep it may as well be a wall. Each added decimal place toward light speed doesn't just take more energy, it takes all the energy. It reminds you of how certain dreams work in life, the kind where the first steps are easy, progress feels fast, but the closer you get to your vision, the more the effort multiplies until you're paying with parts of yourself, rather than just your time or money. There's a point where you have to ask, are you still chasing the goal, or just the idea of finishing? The shimmer ahead remains the same, unchanged by your effort or your cost. It's not a negotiator, it doesn't lower the price for determination. And maybe that's why this moment feels strangely grounding. You're learning, here in the hum and glow of your ship, that the universe's most beautiful limits are also its most uncompromising. You exhale slowly, imagining the wall not as something blocking you, but as a perfect, silent accountant, balancing the books of energy and motion. It doesn't care how much you want it, it only cares whether the equation balances. And right now, the answer is no. You stare at the shimmering horizon, the energy graph still glowing faintly on the console, When a stray thought slips in, maybe particles have already beaten you to it. Not ships, not people, but the smallest pieces of reality, the kind that spend their lives in accelerators and cosmic storms. Some of them seem to play by rules that look suspiciously like cheating. In the quantum world, the speed of light isn't always as rigid as it appears here in your macro-sized, human-shaped frame. There are particles, tachyons in theory, though never proven, that are said to always move faster than light. If they exist, they can't slow down to our speed any more than we can speed up to theirs. Then there are photons in materials, which can appear to outrun light in that medium because light itself has slowed inside it. Even high-energy particles from cosmic rays sometimes arrive at Earth's detectors carrying more punch than anyone expected, as if they've found some back door to skirt the speed limit. Science fact: in certain quantum tunneling experiments, particles appear to move faster than light through a barrier. Though what's really happening is a mathematical quirk. They're exploiting the probabilistic nature of quantum mechanics, not breaking relativity outright. Odd fact: in 2011, the Opera experiment in Italy reported neutrinos traveling faster than light. It made headlines for weeks, stirring excitement and skepticism, until the team found the culprit was a loose cable affecting their timing equipment. The universe, it seems, had not been rewritten, just the wiring. Scientists still debate whether quantum entanglement, where two particles mirror each other's states instantly over vast distances, implies any kind of faster-than-light influence. The consensus is no, since it can't be used to transmit usable information faster than light. But the discomfort remains. If two particles can coordinate without delay, what does that say about the fabric of reality? You imagine these subatomic tricksters zipping past the wall that stops you cold, unbothered by the infinite energy debt you're wrestling with. It's not envy exactly, but there's a sting to knowing that scale changes the rules. Down at the quantum level, particles seem to flit between possibilities without the courtesy of asking permission. Up here, in the heavy, predictable world of ships and bones and engines, the rules are locked tight. It's like watching a child slip through a crowd with ease while you, taller and broader, have to stop and sidestep every obstacle. The child isn't faster by strength. It's faster by existing in a space you can't occupy. The hum of the ship is steady, but your mind is restless. You wonder what it would feel like to shed your mass, to become a point of pure energy with no schedule, no sense of time, free to ride the universe's geometry wherever it allowed. Would it be exhilarating, or would it be unbearable to have no anchor in the familiar flow of seconds? The shimmer ahead doesn't answer, but you can almost imagine it laughing, not cruelly, but knowingly. The universe lets its smallest players bend the appearance of its laws, because those laws are more about what can be measured than what can be imagined. And maybe that's the real game, not breaking the rules but finding the spaces between them. You lean back, letting the thought of those subatomic loopholes fade, and shift your attention to the very thing you've been chasing, the photon. It's easy to think of light as a wave or a particle, as a beam from a flashlight or a sunbeam warming your skin, but right now you try to picture it as an existence. A photon doesn't accelerate the way you do it, doesn't even experience acceleration. From the instant it's created to the instant it's absorbed, it exists in a single, unbroken now. No ticking seconds, no waiting between events. If you could somehow swap places with a photon, your departure from a star and your arrival on Earth would be the same moment. Distance would vanish, because time itself would no longer apply to you. The photon doesn't travel in the way we imagine, it's more like it simply is, stretching between 2 points of space, time in a state that already contains its start and finish. Science fact: from our perspective, light takes time to move about 8 minutes from the sun to Earth. But in the frame of the photon, if it had one, no time passes at all. Its journey is instantaneous in its own reality, which is why speaking of a photon's clock doesn't make sense. Odd fact: light from distant galaxies has been traveling for billions of years, yet for the photons themselves, those billions of years do not exist. They were emitted and absorbed in the same breathless, timeless interval. Scientists still debate how to reconcile this timeless perspective with our own, since relativity teaches that there's no universal now. A photon's reality isn't just hard to imagine, it's fundamentally incompatible with how our time-bound minds work. You picture yourself in that state. No before, no after, no waiting. At first, it's tempting a clean escape from the constant ticking of clocks, from the weight of schedules and deadlines. But then you realize the cost. Without time, there's no change. Without change, there's no story. Every memory you've ever had, every plan you've ever made, all depend on time's slow, steady unfolding. Being a photon might mean freedom from decay, but it also means freedom from becoming. You glance out at the stars, wondering how many photons are striking your ship's hull right now, each one carrying the imprint of where it came from, yet experiencing none of the travel. It's like they're delivering postcards without ever having walked the route. The shimmer ahead feels closer in concept now, if not in distance. You understand a little more about what it represents, not just speed, but a state of being where the very concept of later dissolves. And you find yourself oddly protective of your own slow-moving clock. It's flawed, yes, but it's also the reason you can look forward to anything at all. The hum of the ship folds into the silence between your thoughts, and for a moment you imagine riding a photon's line between 2 points in space-time. Then you blink, return to the rhythm of your own seconds, and feel a quiet gratitude for the luxury of waiting. The thought of living without later lingers in your mind, but then another, stranger image rises, your own reflection caught in the curved glass of the viewport. It's there when you move your head, faint and ghost-like, but something about it feels wrong. Not in a horror movie way, more like it's lagging behind, returning your gaze a fraction of a moment too late. At these speeds, even the act of seeing yourself becomes a negotiation with physics. Reflections depend on light bouncing off you, hitting a surface, and coming back. But here, your velocity is tugging at the journey those photons must take. In your own frame of reference, nothing unusual is happening. You move, the reflection moves. But in another frame, the path those photons take to and from you is skewed, and the timing is bent. At extreme speeds, the delay could be measurable, enough that your image feels subtly misaligned. Science fact. In relativistic motion, the angle and timing of light returning to you can shift due to aberration of light, an effect that causes your field of view to contract forward, almost like a fisheye lens aimed straight ahead. In theory, a mirror placed perpendicular to your motion could return an image that looks distorted in shape and timing. Odd fact. Pilots of high-speed aircraft sometimes report optical distortions in cockpit reflections, not because of relativistic speeds but due to heat, vibration, and slight shifts in the angle of light. Here, you're adding space-time geometry to the list of culprits. Scientists still debate how extreme relativistic aberration would affect navigation using optical instruments. Would a forward-facing camera at near light speed even capture the same arrangement of stars you see? Or would its truth be a warped version of your own perception? You study the reflection more closely, lifting your hand slowly. The ghost hand in the glass rises with it, but the moment feels thicker somehow, like the air between the movement and the mirrored response has gained weight. It's probably only in your head. Your ship isn't moving fast enough to make the lag visible, but the thought hooks itself into you. It reminds you of moments on Earth when you've looked at yourself and felt a disconnect, times when the person in the mirror seemed older than you remembered, or when you caught your expression unguarded and didn't recognize it at all. At high speeds, that disconnect becomes literal. The light that tells you who you are has to work harder to keep up. You lean closer to the glass until your breath fogs it, your own eyes staring back with a faint shimmer of distortion from the curve of the viewport. The wall of light ahead is still there, constant and unreachable, but for a fleeting instant, you wonder if your reflection is already living in a different slice of time, close enough to see you, but not quite the same now. The thought is both unsettling and comforting. If light can carry your image across altered space and time, then maybe some part of you will always be out there, looping back in on itself. long after the rest of you has moved on. The mirror's ghost fades as you lean back, but the unease it left behind stays with you, especially when you glance at the comm panel. It's still blinking patiently, waiting for a signal to send or receive, but you know what would happen if you tried now. Communication, the one thing that feels immune to distance in your daily life, is crumbling under the same rules that make the wall ahead untouchable. At these speeds, even light speed signals start to fail you. It's not that they vanish, it's that they can't close the gap quickly enough to matter. Send a message home and it's like throwing a bottle into a river that's flowing faster than you can paddle. The current pulls the gap open behind you, and the bottle never reaches the shore. The math is merciless. As you approach light speed, the time it takes for a signal to arrive stretches toward infinity. Science fact: in Einstein's framework, no information can travel faster than light. If you're moving away from a receiver at near light speed, the message you send takes longer and longer to arrive, and if you could somehow hit light speed exactly, the delay would become infinite. Communication would be permanently frozen. Odd fact: the Voyager probes, launched in 1977, now take over 22 hours to send a message back to Earth, even though they're moving at a tiny fraction of light speed. It's not the speed alone that matters, it's the vastness of space and the hard cap on how fast information moves. Scientists still debate whether quantum entanglement could ever bypass this limit, but the consensus is that it can't be used for faster-than-light messaging. The entangled particles may react instantly to changes in each other's states, but no usable information is exchanged in that instant. For communication, light speed remains the ceiling. You imagine trying to explain this to someone waiting for your reply. From your perspective, you could speak into the comm and hear your own voice echo back instantly in your cabin. But to them, your words might arrive decades, centuries, or longer after you've spoken. The conversation wouldn't just be delayed, it would be meaningless. By the time your "I'm fine" reaches them, they might not even remember who you are. It makes you think of relationships back on Earth that slowly drifted out of sync, not because of speed, but because of distance in attention, effort, or time zones. Sometimes the gap grows so wide that catching up feels impossible. Here, that impossibility isn't emotional, it's written into the math of the universe. You glance at the shimmer ahead, realizing it's more than a physical boundary, it's a communication cutoff. On the other side, if such a side exists, no message you send could return. It would be a silence so complete that even the thought of being missed would fade into irrelevance. The comm panel keeps its polite blink, as if it doesn't understand what the wall means for it. You reach out and switch it off. There's nothing to say that could cross the widening gulf, and the hum of the ship is enough conversation for now. The comm panel's light fades, and the silence deepens, not the empty kind, but the heavy kind, as though the universe itself is listening. You stare out at the shimmer ahead and realize it's not entirely unfamiliar. Somewhere in its quiet defiance, you recognize the pull of another extreme in nature, the black hole. These cosmic sinkholes are already living at the edge you're trying to reach, their event horizons acting as speed-of-light traps where even photons can't escape. Approach a black hole closely enough, and the effects you've been flirting with out here, time dilation, length contraction, energy extremes, become absolute. At the event horizon, space and time trade roles in a way that makes forward meaningless. From far away, you'd seem to slow to a stop, frozen in place, your light stretched to invisibility. From your own point of view, you'd simply fall inward, crossing the horizon without any special signal that you've passed the point of no return. Science fact: the event horizon isn't a physical surface, it's a boundary in space, time where the escape velocity equals the speed of light. Once crossed, nothing, not matter, not light, not information can get out. Odd fact: if the sun were replaced by a black hole of the same mass, Earth's orbit wouldn't change. The gravitational pull at this distance would be the same. The difference would be that we'd receive no light, only darkness where the sun once burned. Scientists still debate what happens at the singularity, the point at the center where the known laws of physics break down. Some theories suggest all matter is crushed into an infinitely dense point, Others argue that quantum effects might prevent such an outcome. The truth is hidden behind a wall of light, speed, secrecy. You think about the irony. Black holes are places where the speed of light isn't a limit to be reached, but a prison wall no one can climb. To them, what you're attempting is the baseline. Here you are, spending unimaginable effort just to get close, while a black hole sits in some far-off corner of the galaxy, casually enforcing the same condition without trying. The shimmer ahead takes on a new character in your mind, not just the finish line of your own race, but the everyday ground level of these monstrous objects. If you could somehow match speed with light at their horizon, you'd hover there forever in the eyes of an outside observer, locked in a frame of endless suspension. You breathe slowly, feeling the hum of the ship as a tether to normalcy. The wall of light doesn't move, doesn't waver, and now you understand that in some parts of the universe, it's not a destination. It's a permanent state, a gate that never opens, not even for the things that helped make it. You sit with the thought of that black hole horizon, the quiet it holds, and it doesn't take long for your mind to drift toward a question you've avoided until now. If time can slow so much, could it ever run backward? The idea has floated in human imagination for as long as there's been science fiction. Outrun yesterday, curve around the edge of now, and step into the past. But here, with the shimmer ahead glowing like a coin you can't quite reach, the fantasy feels different. The rules of relativity don't forbid playing with time in curious ways. If you could loop around in space-time, like taking a shortcut across a folded sheet, you might land in a different when entirely. Wormholes, closed time-like curves, exotic matter with negative energy density, they all make their appearances in equations as mathematical possibilities. But the universe, so far, hasn't offered an instruction manual for building any of them. Science fact. Time travel into the future is not only possible, it's inevitable. Time dilation, the same effect stretching your seconds right now, is literally a form of one-way time travel. The faster you go, or the closer you get to intense gravity, the further you leap into someone else's future when you return. Odd fact, in 1977, cosmonaut Sergei Krikalev technically time-traveled about 0.02 seconds into the future during his total time in orbit. Minuscule, yes, but measurable a proof that the effect isn't just theory. Scientists still debate whether closed time loops could exist without breaking causality, the principle that cause comes before effect. Some physicists argue that paradoxes would be resolved naturally, with events always adjusting to preserve consistency. Others say that any loop would splinter reality into different timelines entirely, sidestepping paradox by making each version of events its own isolated branch. You imagine what it would feel like to actually loop back, seeing the shimmer ahead, crossing it, and finding yourself not in a new place, but in an old moment. Would it still be that moment? Or would it be a replica, a perfect counterfeit of a past that's already gone? The temptation of fixing mistakes is strong, but there's a shadow to it. If everything is already set, then even your attempts to change the past are just part of it. The ship's instruments hum along, indifferent to your wandering. Outside, the stars are smeared into streaks of blue ahead and deep ember behind. The shimmer remains unchanged, yet in your mind it's now a potential doorway, not just into a different speed, but into a different arrangement of moments. And though you know the odds are vanishingly small, the idea that it might open the way to a different then is hard to fully dismiss. You rest your head against the seat, letting the thought dissolve. Whatever the truth is, the wall won't tell you. It doesn't promise a return to the past. It only waits to see if you're willing to keep moving forward into the unknown. The shimmer ahead has taken on so many identities in your mind, wall, mirror, gate, that you almost forget to consider what it would mean if you actually touched it. If you reached light speed, your body wouldn't behave like flesh and bone anymore. The rules you've known your whole life about mass, volume, and the boundaries between particles would dissolve, replaced by a kind of existence described better by equations than by biology. Relativity says your mass would approach infinity, but that's just the poetic shorthand. In truth, You'd become pure energy in motion, inseparable from the very fabric of space-time. Your molecules, your atoms, your subatomic particles, each one, a packet of mass energy, would be traveling so fast that any distinction between you and the motion would vanish. To outside observers, you wouldn't be a person anymore. You'd be a wave, a streak of energy, a moving solution to a set of field equations. Science fact: mass and energy are equivalent, but their expressions change under extreme conditions. At light speed, the only way to maintain a coherent description of you would be as a distribution of energy, not as a collection of matter bound by familiar forces. Odd fact: the particles created in high-energy collisions inside particle accelerators sometimes exist for only trillionths of a second before decaying into other forms yet in that brief lifespan. They can travel measurable distances at near light speed. For them, existence is an equation's worth of possibility rather than a stable identity. Scientists still debate how consciousness would or wouldn't survive such a transformation. Would awareness tethered to a biological brain simply vanish, leaving nothing but unthinking radiation? Or could information patterns, the structure of thought itself, be preserved in the wave? No experiment has ever been able to test such a transition, because nothing with mass has ever reached the speed of light. You sit in your seat and try to imagine it not as dying but as shedding the anchors of matter. The hum of the ship is still there, the light in the cabin still steady, but in your mind you feel yourself unspooling, each heartbeat stretching into a long, continuous ribbon of energy. There's no breathing because there's no need for oxygen, no hunger, no weight, no up or down, just motion, perfect and uninterrupted. It's tempting, in a way, to be freed from the maintenance of a body, from the limitations of cells and aging, but there's a cost. The warmth of your hands, the pressure of your feet against the deck, the texture of air moving in your lungs, none of it survives that transition. You'd lose the small sensations that make now feel real. The shimmer ahead glows steadily, neither inviting nor warning, but you can almost sense what lies beyond it, not in detail, but in essence. A place where you aren't a passenger anymore, or even a pilot, but the journey itself. You blink, and for a moment, the shimmer feels less like a wall and more like the edge of a map, the place where the chart makers of old would have drawn sea monsters to warn sailors of uncharted waters. Only here, the dragons are galaxies. You've been so focused on your own ship, your own speed, that you almost forgot the backdrop you're moving through. The faster you go, the more the rest of the universe changes, and now you start to notice it. Whole clusters of galaxies are sliding toward invisibility. It isn't that they're moving away from you, it's that you are outrunning their light. Past a certain point, the photons they send will never catch you. From your perspective, the cosmos shrinks. Galaxies that once seemed permanent in your star maps fade toward the red, stretching into wavelengths so long they vanish from your instruments. To you, they're gone, but to the rest of the universe, they still exist, shining as they always have. Science fact: in our expanding universe, there's already a cosmological event horizon, a limit beyond which light from distant galaxies will never reach us, no matter how long we wait. This horizon is about 16 billion light-years away now, and it grows as space expands. Odd fact: because of this expansion, there are galaxies we can see today whose light left them over 13 billion years ago, but if we sent a ship toward them now, that we'd never arrive. They're receding faster than we could ever travel. In a sense, the deep sky is part history, part mirage. Scientists still debate how much of the universe is already permanently beyond our reach. Some estimates suggest that in the far future, every galaxy beyond our local group will drift past this horizon, leaving us in an isolated cosmic island. Others think there might be ways through speculative physics to hitch a ride on the expansion itself. You watch the stars and galaxies ahead contract toward your forward vision, while those behind stretch, dim, and dissolve. The feeling is both majestic and claustrophobic. The universe is massive beyond comprehension, yet at these speeds, it starts to feel like a tunnel. You are in a shrinking bubble of the visible, an island racing through a sea that gets darker at the edges. It reminds you of how memory works, how the further you move through life, the more of the past drifts beyond the reach of your senses. You can recall it, maybe even revisit places and people, but some moments are gone forever, moving away faster than your ability to return. The further you push forward, the more you have to accept that not everything can come with you. The shimmer ahead pulses faintly, or maybe that's just your eyes, but you keep staring, aware now that it's not just a barrier in speed. It's a marker for a deeper truth. The faster you go, the smaller your universe becomes. The shrinking universe outside your window feels emptier than it should, and yet you know it isn't empty at all. Even in the deepest vacuum, there's something an invisible ocean made of restless nothing. You've read about it before. The quantum vacuum, a seething field where particles and antiparticles flicker into existence for the briefest moments before annihilating each other. Normally it's so subtle you'd never know it was there, but at near light speed, subtlety disappears. The ship's sensors begin to register faint, rapid blips, tiny bursts of energy where there should be none. They're not debris, they're not cosmic rays. They're the fluctuations of the vacuum itself, blue shifted into a noisy froth by your motion. It's like flying through an invisible storm that was always there, but now the wind is strong enough to be felt. Science fact: in quantum field theory, even empty space is filled with these fluctuations, called virtual particles. They borrow energy from the vacuum, exist for an unimaginably short time, and then vanish, restoring the energy balance. This process is not just theory, it's been indirectly confirmed through phenomena like the Casimir effect, where two uncharged plates in a vacuum experience an attractive force due to changes in these fluctuations. Odd fact: Stephen Hawking's famous prediction that black holes emit radiation, the so-called Hawking radiation, comes from these same vacuum fluctuations happening right at the event horizon. In that extreme environment, virtual particles can be torn apart, with one escaping into space as real radiation. Scientists still debate what the vacuum really is. Is it a fundamental property of space-time, an artifact of deeper physics we haven't uncovered, or simply a feature of the mathematical tools we use? At near light speeds, those debates stop feeling abstract. The ocean is real when it's breaking against your hull. The hum of the ship takes on a faint tremor now, the motion of the virtual storm seeping into its structure. You imagine each particle flickering in and out of existence like a ghost fish in an invisible sea, brushing against your passage, sometimes colliding, always vanishing before they can leave a mark you can touch. But the instruments know they were there, and so do you. It makes you think of fleeting thoughts, the ones that surface for a second and vanish before you can hold them. Most are nothing, gone without consequence. But sometimes, one lingers long enough to change your course. The quantum vacuum is like that on a universal scale. Most fluctuations cancel out, but in the right conditions, they can shape entire realities. You keep your eyes on the shimmer ahead, aware now that even the cleanest emptiness is not truly empty. Between you and the wall, space is alive in ways you'll never see directly. And as you move faster, the ocean only gets louder. The hum in the hull hasn't faded when the navigation panel throws up a quiet but insistent warning. It's not about radiation or hull stress, it's about your ship's internal positioning system. You frown because GPS doesn't exist out here, but your onboard navigation works on similar principles, timing signals from known sources to calculate your location. At these speeds, the system is beginning to lose its mind. It's relativity again, but now it's gumming up something as simple as knowing where you are. The timing of incoming signals is being distorted by your velocity, arriving out of sync with what your computer expects. The ship can still plot your path, but the corrections grow more extreme the faster you go. The algorithms are working overtime, bending the math to keep your position from sliding into nonsense. Science fact: on Earth, GPS satellites already need relativistic corrections about 38 microseconds per day, because their onboard clocks tick faster than those on the ground, due to both weaker gravity and their orbital speed. Without those adjustments, GPS would drift by kilometers within a single day. Odd fact: When the first GPS satellites went up, some engineers doubted Einstein's corrections would be necessary. The experiment was short-lived. Turning off the adjustments caused positioning errors to balloon almost immediately. Relativity wasn't just theory anymore, it was a line item in the operations manual. Scientists still debate how to handle navigation at truly relativistic speeds. Would you need an entirely new coordinate system, one that shifts with your velocity? Or would you need to constantly recalculate the geometry of space-time around you, mapping a moving landscape that refuses to hold still? You imagine trying to land somewhere like this, relying on instruments that are being lied to by the universe. Even something as simple as left or right could become ambiguous if your measurements can't agree on where the starting point is. The stars outside streak blue and red, their positions distorted by aberration, and you realize your own eyes would be giving you a warped version of reality too. It's a strange kind of vulnerability to be moving so fast that knowing where you are becomes an almost philosophical problem. Are you here, as defined by your ship, or here, as defined by a distant observer? Both can be correct, yet completely disagree. The shimmer ahead doesn't need navigation. It's fixed, not in place but in principle, the one coordinate in all of existence that everyone agrees on, the speed of light. Every other position is negotiable. That one is not. You glance at the panel again, watching the software bend its logic just to keep the map stable. You're still here, for now. But the faster you go, the more here stops being a point and starts being a question. The map holds steady, at least for now, but your ears catch something your eyes can't. It's faint at first, like the hum of the ship is singing in a slightly different key. Then you realize it's coming from outside. Not a voice, not music, but a rise in pitch, so gradual it feels like the universe itself is taking a breath. It's the Doppler effect again, but now it's not just shifting the colors of light ahead. It's pulling the very sound of starlight into a range you can almost imagine hearing. Of course, space has no air for sound to travel through, but electromagnetic waves don't care. If your brain could translate them directly, the stars ahead would be screaming in higher and higher tones, their wavelengths compressed until they moved beyond light and into a violent hiss of gamma radiation. Science fact. If your eyes could see the whole electromagnetic spectrum, you'd notice that as you approach a light source at near light speed, its light is compressed to shorter wavelengths. Eventually, visible light turns to ultraviolet, then to X-rays, and finally to gamma rays, energies so high they can strip electrons from atoms and split molecules apart. Odd fact. Astronomers have detected fast-moving gas clouds in distant galaxies whose light has been blue, shifted so dramatically that it appears entirely different from its original emission, hiding its true source, unless carefully analyzed. Scientists still debate how a craft could survive such an onslaught if traveling near light speed. Layered shielding might work in theory, but at some point, the incoming radiation becomes less like weather and more like a barrage of bullets, each photon carrying deadly energy. The thought makes you shiver not from fear, but from the sheer scale of it. Every star ahead is singing a song you can't hear, but your instruments can. They're not singing for you. They've been singing forever, in all directions, and you're simply moving through their orchestra at a tempo so fast it distorts the score. You imagine slowing down, letting the pitch fall, the music stretch, the colors soften. Behind you, the red-shifted galaxies are humming in deep, slow notes, their wavelengths pulled so long they've dropped below the register of light entirely. You are, quite literally, between songs one too high, one too low, and you are the listener in the razor-thin middle. The shimmer ahead is silent, but now you see it differently. It isn't just a barrier, it's the ultimate crescendo, a point where every note in the universe ahead is pushed to infinite pitch, a soundless climax that no ear, no matter how perfect, could survive. You exhale, the air warm in your lungs, and let the unseen orchestra play on. The orchestra fades, not because it stops, but because your mind shifts to the conductor behind all of it, relativity itself, that patient but absolute hand guiding every note. You've spent so long thinking of the speed of light as a wall, as an opponent, that you almost miss the fact it's also the thing keeping the whole performance coherent. Without it, the rules would shatter. Relativity is more than just a speed limit. It's the stitching that holds space and time together. If different observers couldn't agree on the speed of light, the universe would be a chaos of mismatched events. Your before might be someone else's after, and nothing would be able to agree on what now even meant. Causality, the simple idea that causes lead to effects, would collapse. The speed limit isn't there to hold you back, it's there to keep the story straight. Science fact. Without the invariance of the speed of light, the equations of electromagnetism, quantum mechanics, and even gravity itself would fail. They're all built on the foundation that light's speed is the same for every observer, no matter how fast they're moving. Odd fact. Einstein's original insight came from imagining what it would be like to ride alongside a beam of light. If he could match its speed, he reasoned, he'd see a frozen electromagnetic wave, something Maxwell's equations said shouldn't exist. The only way to fix this was to rewrite the rules of space and time. Scientists still debate whether relativity is the ultimate truth, or just a very good approximation of a deeper theory. Quantum gravity, string theory, and loop quantum gravity all try to go beyond it, but none have dethroned it. For now, relativity remains undefeated in every experiment we've thrown at it. You think about how many human frustrations, traffic rules, bureaucratic systems, even the limitations of your own body exist not to punish, but to keep things from falling apart. No one likes a speed limit until they imagine the roads without one. No one likes the weight of rules until they see what life is without them. The shimmer ahead suddenly feels less like a barricade and more like a guardrail. It's not here to stop you from living. It's here to stop the universe from unraveling under its own contradictions. There's a quiet comfort in that. You shift in your seat, feeling the steady hum of the engines, the glow of the displays, the pulse of your own heart. Everything is in its place because the speed of light keeps it there. You may never cross it, but maybe that's not the point. Maybe the point is that it's the one thing you can rely on, always the same, everywhere you go. The wall doesn't move. It doesn't need to. The thought settles in your mind like a stone at the bottom of a clear pond still, solid and almost comforting. But then another ripple forms. If the wall is there to keep the universe coherent, what would happen if you could somehow break it anyway? Not in theory, but in reality, if you could inject enough energy, find some loophole in the fabric, and punch straight through to the other side. Your first instinct is that it would be catastrophic, like tearing a seam in the hull of the cosmos. Every law you've been obeying would either have to rewrite itself on the spot or collapse entirely. The causal chain of events, the "this happened because that happened," could fracture, leaving effects without causes and causes that never produce effects. Physics wouldn't just stop working, meaning itself would erode. Science fact. In special relativity, surpassing light speed would reverse the order of events for some observers. An action you take could appear to happen after its consequence somewhere else. This isn't just confusing, it's logically inconsistent, creating paradoxes that make physical reality unstable. Odd fact. Some speculative theories about tachyons, hypothetical particles that always travel faster than light, suggest they could be used to send messages into the past. But those same theories show how such communication could lead to paradoxes, like receiving an answer before asking the question. Scientists still debate whether superluminal travel is impossible or merely impractical. Wormholes, warp drives, and other exotic ideas skirt the problem by bending space-time itself, allowing you to arrive somewhere faster than light could without technically breaking the limit locally. But even these would require conditions: negative energy, stable exotic matter that may not exist. You imagine it though. The shimmer ahead tears, not like glass but like the surface of water, rippling apart to reveal a landscape that isn't just faster, it's other. The stars might blur into an undifferentiated glow, distances collapsing entirely. You might move so far ahead of the universe's own unfolding that you see events no one else will witness for billions of years or worse. See events that will never happen at all. The temptation is there, not because you think you could handle it, but because there's a part of you that can't resist peeking behind a locked door. It's the same instinct that drives explorers into dangerous terrain and scientists to run experiments they know might fail. Curiosity doesn't care about comfort. The hum of the ship feels heavier now, as though even it understands the gravity of the thought. You watch the shimmer, wondering if somewhere, somehow, something has already crossed and is looking back at you. Maybe it's not a wall for everything, maybe it's just a wall for you for now. The shimmer ahead has been everything in your mind. A finish line, a guardrail, a locked door, and now, with the idea of breaking through still lingering, it begins to feel like something else. A guardian. Not the kind that blocks you out of spite, but the kind that stands watch, because there's something on the other side you're not meant to drag back with you. You think about how light speed isn't just an arbitrary line in the sand. It's a condition that holds the whole structure of reality together, like the tension in a spider's web. Pull one thread too hard, and the pattern unravels. If the wall fell, what would spill through? Would you suddenly find the universe filled with contradictions, every possible timeline colliding into a single chaos of events? Or would it go the other way? Would reality simply stop updating, frozen in a frame your speed had outpaced? There's a part of you that thinks the wall's job is less about stopping you and more about protecting everything else. Science fact. The cosmic speed limit keeps cause and effect ordered, ensures that energy and momentum remain conserved in every frame, and maintains the same physical laws across the observable universe. If this limit didn't exist, the symmetry that physics relies on Lorentz invariance would break, and with it, much of modern science. Odd fact. Some versions of quantum gravity predict that at incredibly high energies, the speed of light might vary slightly. If true, it would mean the limit we know is a local feature of our universe's current state, not a universal constant for all possible realities. It would also mean the rules could be different elsewhere. Scientists still debate whether these exotic scenarios are worth taking seriously or are mathematical curiosities with no real-world counterpart. The frustrating part is that testing them would require energies we can't even imagine producing, much less controlling. You shift in your seat, looking at the wall now as something less like a race you're losing and more like a treaty you agreed to without reading. You've lived your entire life under this limit. Every thought, every action shaped by a speed you've never come close to. And now, brushing against it, you're starting to see the fine print not as a punishment, but as a design. It makes you think about the limits in your own life, the ones you hated, until you realized they were the very reason the things you cared about still worked. Not all boundaries are cages. Some are scaffolding, holding up a structure you didn't know you were living inside. The shimmer doesn't brighten, doesn't dim. It doesn't have to. It has the quiet certainty of something that's been here since the first second of the universe and will be here long after the last. You breathe slowly, and for the first time you feel less like a challenger at its gates and more like a guest who's been allowed to come this close. You let your gaze soften, and the shimmer ahead stops being a sharp-edged wall. It becomes a horizon again, fluid, unreachable, but no longer taunting. The hum of the ship, the faint vibration in your seat, the slow rhythm of your breath, they all seem to merge into the same quiet background, as if the universe itself has decided to let you rest here. You realize you're no longer trying to reach it. You're simply sharing space with it, the way a person might sit at the edge of the ocean, knowing they'll never drink it dry. The rules that brought you here haven't bent. Your speed hasn't changed, but your perspective has. The limit isn't about keeping you out, it's about keeping the universe in. Every star behind you, every galaxy shrinking at the edges of your vision, every piece of matter holding its shape owes something to this ceiling you can't break. Without it, the story of the cosmos would lose its sequence, its order, its ability to make sense. And maybe you too would lose something, the sense that your journey means anything at all. Science fact. The speed of light is woven into every physical constant. We know Planck's constant, Newton's gravitational constant, even the equations for electromagnetism. It's not just a number. It's a thread tying all of physics into one tapestry. Odd fact, even if the universe lasted forever, you could spend all of eternity accelerating and still never touch this horizon. It's not a matter of persistence, it's a matter of the rules themselves. Scientists still debate whether there's any meaning in limits beyond the physics, whether the universe's structure has a purpose or is simply the result of blind chance. Out here, with nothing but the shimmer ahead and the trail of red-shifted light behind, the question feels less like a debate and more like an invitation to be okay with not knowing. You close your eyes, not in defeat, but in surrender, not to the wall, but to the understanding that reaching it isn't the point. The point is moving toward it, learning what changes in you along the way. You can almost feel the stars behind you exhale as you ease back from the throttle, letting time and distance relax into their usual rhythm. The shimmer is still there when you open your eyes, as calm and constant as it's always been. You give it a final glance, not as a challenge, but as a thank you. Then you turn your attention to the controls, ready to drift back into the slower universe you came from. In this journey, you approach the speed of light not as a number on a dial, but as a living boundary in the architecture of reality. You felt the mass in your bones grow stubborn, the seconds in your clock stretch thin, and the colors of the cosmos bend into strange new languages. You watched space itself narrow into a tunnel, the background hiss of the Big Bang grow louder, and the quiet truth of Einstein's equations settle into your mind. Along the way, you imagined photons living in a timeless now, quantum particles flirting with loopholes, and black holes existing effortlessly at the horizon you could never touch. You learned that this speed isn't just a barrier, it's the thread holding the universe's story together. The reason cause and effect still makes sense, and in the end you understood that crossing it isn't necessary to know its worth. The shimmer ahead remains, not as a taunt, but as a reminder. Some limits aren't meant to be broken, they're meant to be honored. You rest in that knowledge, the hum of your ship fading into the deep, and you let the universe keep its secret while you keep moving gently within it. Good night.